Hello chemists, this is Ms. Placino and you are watching Screencast 7.4 on phase changes. Today we're going to talk about what happens to the particles of a substance as it undergoes different phase changes. To review, I want to talk about the 6 phase changes that we're going to cover. Hopefully it's fairly obvious from the pictures that this at the top is supposed to represent a solid. In the beaker we have a liquid, and in it looks like a volumetric flask, we have a gas. Now by altering the temperature and pressure conditions, we can get any of the 6 phase changes to occur. We can go from a solid to a liquid, which you know is called melting. We can go from a liquid to a gas. We'll call that evaporation. You can also call it boiling or vaporization. Usually that's just kind of differentiating or distinguishing how much energy is being used to force that change to occur. We can go from a gas to a solid, one of the more exotic phase changes. This is the one that students always forget. It's deposition. Something like water vapor in the atmosphere, when it gets cold and it touches something like a windshield or a blade of grass, is going to deposit itself immediately as frost without becoming a liquid first. We can go in the opposite direction. Solids can become gases. That process is called sublimation. Something like dry ice, which is frozen carbon dioxide, is going to sublime. Basically, it's called dry ice because at atmospheric pressure, carbon dioxide cannot exist as a liquid. So it goes directly from a solid to a gas, it sublimes, and at no point in time is it going to leave a puddle. If we go from a gas to a liquid, that's called condensation. And finally, going from a liquid to a solid, it's going to be solidification, or if you'd prefer, freezing. All right, so hopefully no surprises here, and you remember this from earlier in the semester. Just to kind of add a new thing to it, I want to talk about endothermic and exothermic. So let's do exothermic first. Maybe not. Yeah, this is being stubborn today. Exothermic and endothermic. Now these are terms that you might not have come across before, but we can break it down. We have exo and therm, we have endo and therm as well. Exo means out, and therm is referring to heat. So in an exothermic change, heat goes out, or in other words, heat is released. So when an exothermic phase change happens and heat or energy is released, the motion of the molecules is going to slow down. If you look at endothermic, endo is kind of meaning in. Thermic or therm is again referring to heat. So these are going to be changes where heat is absorbed. So if heat or energy is absorbed by particles or molecules, whatever you'd like to think of them as a substance, you can imagine that those particles are going to start moving a little bit faster, depending upon how much energy they were able to absorb. So what I'd like you to do is pause the video, go through and see if you can identify, I guess classify might be a better word, each of the phase changes as being exothermic or endothermic. So pause me and try it. All right, let's look at the phase changes between solid and liquid first. If I start as a solid and I melt and become a liquid, my molecules are moving around a little bit faster. They've got more freedom to move. This looks like it's going to be an endothermic phase change. It takes energy to get a solid to melt. If the process of going from solid to liquid is endothermic, the opposite, freezing or solidification, must be exothermic. And hopefully that makes sense. You put things like that you want to freeze, like when you make ice cubes, in the freezer, and you try to get rid of all that extra heat. Slow those particles down and force them into a solid arrangement. If we look at condensation and evaporation, well, condensation, we go from a gas, which has a lot of energy, over to a liquid, lower in energy, so it must have released heat. Exothermic. Evaporation, it takes energy. Oops. What am I doing? There we go. It takes energy to get a liquid into the gas phase. If you want to boil water, you know that you have to put it on the stove and get a flame underneath it. You are providing energy to the liquid. And finally, deposition and sublimation. Deposition is definitely exothermic. We've got to release a lot of heat or energy to go from a gas to a highly structured solid. And sublimation, that's going to be the opposite. That's going to require energy. So Again, exothermic is meaning heat goes out or heat is released. You can think about that as the particles or molecules of a substance moving more slowly. And endothermic is the opposite. Endo means in, so this is heat being absorbed, and that's going to cause our particles to move faster. In some of the phase changes that we're going to talk about, or the different topics that we're going to discuss in this video, we have two different phases existing in what's called a dynamic equilibrium. This is a term that you should have come across in your reading last night, but I'd like to talk about it in a little bit more detail. In dynamic equilibrium, you have two opposing processes, or two things that are the opposite of each other, occurring at exactly the same rate. So if I show you this GIF, or however you say it, hopefully you can figure out pretty quickly what the two opposing processes are. It's definitely water coming in, and that seems to be equal to the rate of water going out. How do you know that these rates are essentially equal? Well, if you look at the water level in the boat, it appears to not be changing. So the rate of the water coming in must be exactly equal to the rate that this guy is bailing water out. Now I can shift this equilibrium by, maybe this guy smartens up and he stands on the hole or gets a bigger bucket, he can bail more water. Or maybe the hole gets bigger, and that's going to cause water to come in faster, and I can shift that equilibrium. But we will discuss that in a lot more detail in the spring semester. For the time being, this is just kind of the picture that I'd like you to think of for dynamic equilibrium. Two opposing processes happening at exactly the same rate, so that the overall picture doesn't really change. In this case, the water level and the boat is staying the same. If you take a liquid, something like water, and you seal it in a container, eventually your gas phase and your liquid phase, or your vapor phase and your liquid phase, are going to establish a dynamic equilibrium. So what's going to happen? Initially, you'll have your liquid, and some of these little liquid particles or liquid molecules are going to end up vaporizing or evaporating and becoming a gas. There they are over here. Eventually, you'll get to a point where some of those gas particles are going to condense and reform a liquid. And if you give this enough time and you keep the system closed, you can imagine if I take off one of the corks, all of a sudden all those gas particles are going to escape. That if I keep this system closed, eventually the rate of evaporation will be equal to the rate of condensation. And when that happens, if I take the pressure of the gas that's in that system, that is my vapor pressure. So the vapor pressure is simply the pressure by a vapor in equilibrium with a liquid phase at a given temperature. If I change the temperature, I'm going to kind of shift that equilibrium. For example, if I make it hotter, you can imagine that that's going to cause more of these little particles to evaporate. If I make it colder, then condensation is going to take over. But if I can keep that at any temperature and keep it steady, I will eventually establish this dynamic equilibrium, and I will get a vapor pressure that will be temperature dependent. Some substances are very volatile, and that basically just means turns into gas easily. And things that turn into a gas very easily have high vapor pressures. That means at equilibrium, we're going to have a whole bunch of particles in the gas phase. Oh, that's awesome. My neighbor is not taking care of their car alarm. We also have non-volatile substances. They're going to have low vapor pressures. In other words, when we have this dynamic equilibrium established, there are going to be relatively few particles in the gas phase. So this is really based on intermolecular forces. Which one would you expect to have strong intermolecular forces? Volatile substances or non-volatile substances, and why? If you're thinking non-volatile are going to have stronger IMFs, you are correct. Something like water is very non-volatile. It tends to have a relatively low vapor pressure. We know that water exhibits hydrogen bonding, which is the strongest intermolecular force. Volatile substances are going to have weaker intermolecular forces. For example, I bet you opened up a bottle of rubbing alcohol, or you've had to open up one of those little alcohol wipes to clean something, and you can immediately get hit with that smell of rubbing alcohol, isopropyl alcohol. That's because isopropyl alcohol doesn't have quite as strong intermolecular forces, and it's going to be easier for it to enter the gas phase. Here's an example of a vapor pressure curve, and you have this in your reference table that has another line on there. I think it's table H. Basically, boiling is going to occur when the vapor pressure is equal to the atmospheric pressure. So you can picture the atmospheric pressure. Let's draw like a little beaker of water. Is pushing down on top of the water, and vapor pressure is pushing up. When the vapor pressure equals the atmospheric pressure, then those particles or molecules of liquid are going to be able to escape and enter the gas phase, hence boiling occurs. So we know that 760 torr is equal to 101.3 kPa is equal to 1 atmosphere. So this is boiling point. So the way I'd use this chart is I would get my pressure. I can trace it over to the substance I'm interested in at atmospheric pressure. I can follow that down. I can see water is at 100 degrees. So that's telling me that water boils at 100 degrees. No surprises there. As the atmospheric pressure changes, water is going to boil at different temperatures. If you're somebody who does a lot of baking, you might have seen from time to time high altitude instructions. And you bake things and cook things in general slightly different when you're at high altitudes because things like water does not boil at the same boiling point. It's going to boil at a lower boiling point. You can see that as the pressure drops, so does the boiling point, which makes sense. There is less of the atmosphere kind of weight pushing down on the substance you're trying to boil, so it's going to require less energy to get things into the gas phase. Ooh, let's do some practice. So let me get to the other screen. All right, so for all those questions, you're going to need to use table H. So I'm going to pull up the questions and I'm going to kind of toggle back and forth between the two of these different files, I should say. All right, so phase changes. What is the boiling point of ethanol at 101.3 kPa? So let's go ahead and get back to our reference table. We're interested in ethanol at 101.3 kPa. So here we've got our vapor pressure. We've got 101.3 kPa already marked off. We can just kind of trace that line across until it hits ethanol. And let's trace it down. One of the most common mistakes people make with this chart is just really not reading it correctly. Make sure that you got the tick marks on the axis measured off or counted off correctly. They're by 5s on the x-axis and they're by 10s on the y-axis. So at a pressure of 101.3 kPa, it looks like we're going to see ethanol evaporating or boiling at about 79 degrees Celsius. So let's go back. I'll say 79 degrees Celsius. What does the atmospheric pressure need to be in order for propane to boil at 40 degrees Celsius? We'll do this one together, and I'll leave you the other ones to play around with. So now I want to look back at my reference table. I'm interested in propanone, boiling at 40 degrees Celsius. So I've got my propanone line. I know that this is 40 degrees Celsius. So I'm going to trace up. I'm going to trace over. And again, on the y-axis, each tick mark is representing 10 kPas. So when I look at this, I see, maybe 58 or so kPas. So I highly recommend going through and just finishing this up, work on the practice problems, and make sure that you feel comfortable using that chart. This is what we call a heating curve. Heating curves and cooling curves, for that matter, are simply showing how a substance responds to either being heated or cooled. You can tell that this is a heating curve, first because it tells you heat absorbed. So we know if something absorbs energy or absorbs heat, it's going to increase in temperature. We kind of see this general trend going up. Also, you can just kind of look at the trend. Yeah, it's increasing in temperature, so this must be a heating curve. If we have water, let's say, and it's at anywhere from negative 50 degrees Celsius to 0 degrees Celsius, we know that it's going to exist as a solid. Once we cross 0 degrees Celsius at 1 atmosphere pressure between 0 and 100 degrees Celsius, water is going to exist as a liquid. And finally up there at the top, over 100 degrees Celsius, water is going to exist as a gas. So hopefully no surprises there. When we're in phase, adding more energy is going to cause an increase in temperature. The interesting parts of the graph, or this chart I should say, are the flat parts. These are the places where we are putting energy into the system, and it's not really matching up with any sort of corresponding change in temperature. What's happening at this point at 0 degrees Celsius between solid and liquid? Well, this is where melting is occurring, and we call this delta H sub F. This stands for heat of fusion. So basically, you could just think of that as energy to melt. You might be able to guess that that really long flat line is going to be the energy required to evaporate or vaporize. We call this delta H sub V. Energy to vaporize. At these places, instead of having that extra heat that's being absorbed turn into a change in temperature or change how quickly the molecules are moving around, that energy is being used to do something else. Pause the video, see if you can figure it out. What's going on with that additional energy that's being added in? During a phase change, whether we're talking about melting, vaporization, sublimation, deposition, any of them, the molecules themselves are not changing, but the way they are arranged or organized in relationship to one another are changing. As we go from a solid to a liquid, what's happening to our intermolecular forces? They're starting to be weakened. A solid has very strong intermolecular forces and holds those particles in fixed rigid locations, where a liquid is going to have slightly compromised IMFs, and those particles are going to be able to move around. So at these places, we are weakening the intermolecular forces. At vaporization, that takes a ton of energy to vaporize. Here, we're destroying intermolecular forces. We've got to make sure that they are weakened to the point where the molecules are able to escape that attraction of one another and become a gas. This is a heating curve for water, but it's going to be pretty similar for most substances, most molecular substances. You're going to see it relatively easy, comparatively speaking, to vaporizing. Less energy is required to melt than it is to vaporize, and it's all about what's going on with the intermolecular forces. All right, the last thing I want to talk about today are phase diagrams. This is something that you'll see like on the SAT too, but it doesn't generally show up in a typical sophomore chemistry class. A lot of times when we're thinking about phase changes, people have the tendency to think only in terms of temperature, but the reality is you can also get phase changes to occur by changing the pressure. That's something that's a little bit more difficult for us to do at home or in the lab, at least our lab anyway, but it is possible. So in a phase diagram, it's showing the relationship between pressure and temperature for a solid, a liquid, and a gas. So I can get between phases simply by changing one or both of these variables. If I go from a solid to a liquid, this line must be representing melting. That same line, if I'm going in the opposite direction, is representing freezing. Now, the same dual purpose for these lines can be represented of solid to gas. We can have sublimation and deposition. We can also have evaporation and condensation between a liquid and a gas. There are 2 points to be aware of. One of them is the critical point. This is really the point where there's just so much temperature, or such a high temperature and comparatively speaking, pressure where it's going to be nearly impossible to condense a gas, or for all practical purposes impossible. So we can't really distinguish between the two phases. The triple point is where we have all three phases of matter existing simultaneously. And that may initially not seem like a really big deal, but it's actually a really unique point. And I want to show you a quick video of that. Ooh, this is going to be a long screencast. Sorry, guys. All right, so here we're going to do a triple point demonstration using a type of alcohol, and we're going to use what's called a standard vacuum setup. Basically what happens is you put a bell jar over your substance in an Erlenmeyer flask, and you just start sucking out all of the air. So the pressure is going to drop substantially, and this is happening at about room temperature. Just by lowering the pressure, we can get vaporization to occur. We got this boiling. If you were able to touch it, it's going to be at room temperature. Things don't have to be hot to boil. Just the atmospheric pressure and the vapor pressure have to be equal. So if we keep dropping the atmospheric pressure, vapor pressure is going to allow this to boil. So this happens, as you can see, shortly after we start pulling the vacuum. And it stops. We're just going to keep on pulling the vacuum. 2 minutes later, the triple point occurs. So if we look carefully at what's going on in the video, you can start to see that it is freezing. And while it is freezing, it's also starting to boil. So this is really, really strange. We've got a solid forming from a liquid, we've got a gas forming from a liquid, things are subliming, condensing, evaporating, depositing. You got a lot of stuff going on in there, and that is the triple point. It's a really kind of weird place. You're only going to find it in a lab. Things aren't going to hit their triple point under like regular atmospheric conditions. And if you continue to pull the vacuum, you're just going to move off the triple point eventually, and that's what has happened here. Ooh, all right, I guess that does it for today. Sorry I ran a little long today, guys. Thank you for tuning in, and I hope you found this helpful.